Good morning, good afternoon, and good evening, everyone. I hope you're all doing safe and healthy. Thanks for joining this virtual format of IEEE Ethernet IP Automotive Technology Week. My name is Prathap Venugopal. I'm here to present the talk on fault tolerant Ethernet time synchronization, prepared together with my colleague Soheil Samii. In this talk, we will start with the need for time synchronization and benefits of time synchronization for ADAS and automated driving systems. We'll discuss the various ways that today industry implements time synchronization. And specifically, we will talk about how it is implemented on the Ethernet-based electrical architecture. We will then discuss on why do we need fault tolerance in Ethernet time synchronization, and we'll discuss about the challenges and limitations of implementing fault tolerance with the 2011 version of IEEE 802.1.a standard, and how these limitations can be resolved with the just released 2020 version of 802.1.as together with AUTOSAR-based time sync protocol. And we will conclude the presentation with how the TS and automotive profile can help in implementing this in the right systems. Let's move on to the presentation. What is time synchronization? It is a process of coordinating independent clocks in a system or a network into a common time. And this timing could be a global time or a relative time to the just system. So how does time synchronization help in ADAS and automated driving? First, time synchronization enables time stamping of sensor data packets, which helps in accurate perception of the environment. If all nodes are synchronized, the system can trigger sensors to capture the environment at the same time, and this significantly reduces the amount of computation needed in sensor fusion software. And application softwares and different software components can be executed in a synchronized way. If this and if the system is synchronized to an absolute time, this will enable whole possibility of using not just in-vehicle sensor data, but also from cloud, vehicle to vehicle, or even vehicle to infrastructure based sensor data for the automated driving. And finally, state changes and error events or logs can be timestamped. This will enable precise diagnosis of failures. So studies have shown that average human driver reaction time is between 500 to 750 milliseconds. Race car driver seems they can react as fast as 200 milliseconds. What does this mean to a vehicle? Let us imagine a scenario where the vehicle is traveling in 85 miles per hour in a highway, and this is the top speed limit in US. If we take average human reaction time of 500 milliseconds, uh, at this speed, the vehicle would have traveled about approximately 62 feet or 20 meters. And this is about 4 lanes when you look into horizontally. In complex scenarios like debris coming from the vehicle ahead or current scenarios, this distance could be extremely dangerous and it could be fatal. And not just this in highway scenario, sometimes even the urban scenarios could be could be an extremely complex driving task with all these pedestrians, cyclists, and then the slower speed limits. So how much time does an automated driving system has? Here is a simpler representation of an automated system with different elements like perception, path planning, and vehicle control. So when we design such a system, the system needs to execute the whole sequence of sensing, perception, path planning, vehicle control, and the actual control at least equal or should be better than the average human reaction time in these scenarios with complex environments. This is another view of the system with time progression. In this system, imagine few sensors and their firing time is totally controlled by their local clocks. Similarly, algorithms in fusion, path planning, and vehicle control runs on their own schedulers based on their own local clock. If we have a system like this, first of all, there will be a delay in starting the perception until every sensor comes online. Even when all of them are starting on time, the anarchy due to lack of synchronization will result in lack of control on the local clock drift. And with the unsynchronized capture, deriving the accurate perception will result in high computational resources consumption to execute any fusion algorithm. Therefore, time synchronization is an absolute need for efficient automated driving system architecture. We already have heard the significant benefits in the introduction session. An industry has recognized these benefits early and has been implementing time sync for a while. How is it done today? So far, systems have been realizing time synchronization in a combination of both standardized and proprietary implementations. In vehicles, time synchronization was implemented only for a particular domain, like infotainment and body. Mostly, these were custom solutions. For example, we use a GPS clock as the source, and current time is sent over CAN every second without even any protocol mechanisms for time synchronization. We've also seen NTP being used in prototype vehicles. We've seen PTP or IEEE 1588 in early infotainment systems. And our GM's level 2 Super Cruise systems use a local time based on flex race time base. We know that most of today's and future automated driving vehicle sensor network will be based on Ethernet. And since the introduction of AVB and TSN in automotive, this industry has been using IEEE 802.1.AS 2011 standard together with a venue profile for time synchronization in both infotainment and active safety use cases. In some of our current AVs, we use 802.1.AS 2011 with BMCA or the IEEE mode. Um, and the sensors and endpoints in most of these networks, they use AUTOSAR-based time synchronization protocol. And we've seen IEEE standard has been used widely today. We understand the benefits of time synchronization, but why is it required to be fault tolerant? We already learned that the synchronous sensing and synchronous execution helps in reducing computational complexity. So that's a good motivation. But even if synchronous sensing and execution is not used, software components like sensor fusion, which would require time synchronization availability, need to be fault tolerant for certain amount of automation levels and operational domains. Furthermore, future electrical architectures that support higher level of automation will primarily based on Ethernet backbone. Guaranteed delivery of higher priority traffic may require time-triggered communication. Additionally, some of the Ethernet time-sensitive technologies like 802.1 QBV and 802.1 QCH will require uninterrupted high accuracy time synchronization as the basis. So fault tolerant time sync is the foundation to redeem these incentives. How to realize fault tolerance with Ethernet time synchronization? Let us see what are the possible faults that could arise in today's time synchronization. A link or bridge can fail, a grandmaster could fail, or sometimes the grandmaster could be very unstable. How are we solving this problem today? Link failures and GM failures can be detected, and as a fail-safe action, another grandmaster could be selected by enabling the best master clock algorithm when we have more than one grandmaster capable devices in the network. This may address both the grandmaster failure and the link failure to some extent. But this method has its own limitations. Number one, currently there is no inbuilt mechanism to adjust the time jump that could occur during the secondary grandmaster selection process. Number two, the process of selecting new grandmaster by using best master clock algorithm during the failover takes multiple seconds, and not to forget the time it takes to detect the failure on first. What is the impact of this? Let us take an example clock tree in which the clock depth level is 5. With the data we captured through a bench-based experiment, it would take a maximum of 15 seconds, and by this time, local clocks in slaves that comply with the 100 ppm requirement would have already drifted by 1.5 milliseconds. 1.5 milliseconds may not sound significant, but when this timing is basis for time trigger traffic and synchronous task execution, the ripple effects could be precarious. But there is some good news. The 2020 version of GPTP seems addressing these challenges. Let us see how. First is how to address the link failure. 802.1.AS 2020 version of the standard introduces multiple clock domains, and by utilizing time domains and configuring the routing path accordingly, we can overcome link failure. Here is a sample implementation with one grandmaster and two clock domains. Domain 1 is configured in this path, and domain 2 has been configured in this path. So in this example, even in any of these links, L1 to L4 fails, all these endpoint or end stations can switch to a secondary domain in case of failure. Now, in a normal operation time, each of these link would receive two different clock domains. And how to deal with that? Order based time synchronous solution, synchronous time based manager could be of help in this case. And what is this logic of implementing it? In the same network example, let's take the node E1, which receives the both time domain 1 and domain 2. And let's see the time domain 1 is the primary one. And when in case of any of these links or L1 or L2 fails, the E1, the endpoint 1, end station 1 can choose the secondary domain, time domain 2 in this case, whenever it detects almost seamlessly. Similar logic could be implemented for any endpoints and its failures mode. So we have seen how to address the link failure. How does the standard addresses the grandmaster failure? Backup grandmasters can be configured with domains in addressing the grandmaster failure. Once the primary grandmaster fails, the secondary grandmaster can be chosen by any of these nodes. In the same network, let us consider there are two grandmasters, primary and secondary. Let's assume the primary one is assigned to the domain 1 and secondary is assigned to the domain 2. In case of primary grandmaster failures, any of these node could endpoints could switch to the domain 2 instantaneously. And this example shows one clock tree per grandmaster, and this we could also have the similar configuration where one grandmaster can have two different clock trees, just like our previous examples, and several other configuration is also possible. So this addresses the grandmaster failures, but what about the time jumps happens during the switchover? It is important to synchronize both primary and secondary grandmasters, if not during the startup, but once the system is stable. So once this is synchronized, this would prevent the time jumps during the switch between the primary and secondary grandmasters. And of course, endpoints shall need to arbitrate between the clock trees during the normal process and also during the failover. So how do we implement fault tolerance in an AUTOSAR-based endpoint system? In order to understand that, we need to know a little bit about AUTOSAR time synchronous protocol. This protocol originally started with CAN-only solution, but now the current version of the standard is completely aligned with IEEE 802.1.AS 2011 standards, with some limitations and extensions when compared to the IEEE one. For example, it doesn't support BMCA, something similar to the Avenue profile. And by using AUTOSAR specific TLV, this protocol extends the GPTP message format to add checksum, VLAN support, etc. And AUTOSAR time sync systems inherently support multiple time domains. And not just that, it extends the time synchronization over to other non-Ethernet protocols like CAN and FlexRay as well. So here is an example of implementing this logic in AUTOSAR-based instance. AUTOSAR modules will receive the global time from both domains in the same example. AUTOSAR's STBM or Synchronous Time-Based Manager module shall implement the logic of choosing the secondary domain either during the link failure or grandmaster failure, or even in case of grandmaster instability event. Since AUTOSAR already supports more than one time domains, the arbitration logic to choose this can be implemented as per our initial study. But there should be a detailed bench-based proof of concept that is required to assess if further extensions are required for the current standard. So we know that the 2020 version of this standard, IEEE standard, supports multiple time domains, and AUTOSAR-based time synchronization can help in implementing the logics in the endpoints. But can we just use 2020 standard as a whole for all the different automation levels? To answer this, the TSN automotive profile helps in great cause. TSN 802.1 DG task group has already created both base and extended profiles. In lower level automation systems, the driver should always be in the loop. In case of failure, in most of the driving domains, the system needs to perform the task until few seconds. For this, the base profiles time synchronization requirements like optional BMCA and single time domain could be sufficient. But for higher level of automation and in certain complex driving domain with even lower automation levels, the system needs to be in charge of the vehicle for longer period of time in case of multiple seconds, and it could be even minutes until it reaches the minimal risk conditions. 801 DG's extended profile seems promising. It supports multiple time domains, which is the foundation for fault tolerant time synchronization. So in summary, IEEE 802.1.AS 2020 provides seamless redundancy with hot standby for the Ethernet-based electrical architectures. Ongoing 802.1 DG TSN automotive profile shall define the right profile with the associated TSN technologies. Endpoint should be capable of executing time synchronous tasks and clock domain arbitration during a grandmaster failure. AUTOSAR time synchronization protocols provide these capabilities. Vendors may choose to adopt these for sensors and other endpoint ECUs. To conclude the presentation, fault-tolerant Ethernet time synchronization is the foundation for highly automated driving systems with complex driving domains. It is also the basics for synchronous sensing, synchronous execution, and a basic protocol for TSN protocol suites. An Ethernet network that has IEEE 802.AS 2020 standard, together with AUTOSAR-based endpoint, is recommended for higher level of automated driving systems with complex driving domains. An IEEE 802.1 DG TSN automotive profile will help in choosing the right TSN protocol suite for the right level of automated driving systems. And that concludes my talk. Thank you very much for listening.